Welcome back for part two. Let's move me down so we can get more jellyfish there in the picture. Yeah. Okay, let's look at the UPGMA method. Yeah, that's who invented it. You don't need to know that, but if you do need to know that, there it is. I am not going to test you on that. That's all I'm saying. And 1958, so this is right as genetic evidence is just about to become available or just starting to become available. So really, really early stuff. Okay, and fine. Let's consider some sequences whose distances can be represented as points in a plane. You say, how do I do that? And the answer is a computer can do that. You and I may find that harder to imagine, but let's just assume that there's a center point and each mutation you make moves you like an inch out from the center point. And so the center point will be like the average of all 5 sequences. And so you say, okay, how far do we have to go out to get to this sequence? And then if you have 2 sequences that actually join together, like they follow the same evolutionary path, then that's fine, something like that. But we'll start grouping them later. So we'll imagine these things. It's just like a phylogenetic tree, and it's just we're going to put it flat on a piece of paper, like it's on a plane. Great. Yeah. So we could also represent those as a distance matrix. So by distance matrix, that means you take the genetic distance between each sequence and each other sequence. And the idea is, of course, that sequences that are close to each other in some meaningful way should have more in common. So they should have fewer changes, so they should have less distance between them, and therefore more similarity between them, right? Yeah, that kind of makes sense, I think. So yeah, some will be close, some will be far, and UPGMA is going to cluster these sequences. Let's see how. Okay, you're going to start by making this distance matrix, or rather the computer is going to start by making the distance matrix. You could do it, it would just take you a while. And in the early days, it probably was done, could be done by hand anyway. Or maybe by punched cards on a ancient wooden computer. I don't know. Yeah, the 50s were weird. I guess they had some sort of computers then. Let's see. We're going to identify the groups with the smallest distance between them. So that's what it means here when it says the least dissimilar. It seems like a double negative, but yeah. Least dissimilar groups, which means the most similar. But we're not looking at similarity. We're looking at differences, and we're looking for the smallest difference. You get to the same place, but we're being precise about the method that we're using. Okay. And then if there are several that are equally distant, UPGMA will pick one at random. And then it can refine that later. It kind of works, but right there you can see a little element, like a little tiny seed of doubt, like, oh, is this the best way to do it? It's the way that works, because you don't want to say, oh, we have no answer for you. These two things are, because our algorithm is wrong. I guess it is a way to get around a fundamental limitation of a distance-based matrix. Yeah. Because if two things are equally distant from each other, then what else are you going to do? It would make sense to, group both of those things at the same distance. But, yeah, that may be harder to do with a particular algorithm. So it's not a problem with nature, it's a problem with the computer program that's running it. And so they're solving it in this kind of arbitrary way that adds a little bit of uncertainty into your model, basically, or a little bit of error in. But we're trying to add a little error to avoid having no answer. Yeah, is the idea. Okay, we're going to take the 2 that have the smallest distance between them. So let's say operational taxonomic units, like sequence 1 and 2, whatever you are, have the smallest distance. That's great. We will then basically draw a circle around those. And we'll combine those to make a cluster. And then we'll make a new distance matrix. And instead of using those 2 sequences, we're going to combine them. And so we'll say the new sequence of this cluster is halfway between those 2. That's the unweighted mean part of it. We're just going to take the average of these 2. which is kind of a weird concept, right? You say, well, this one has an A nucleotide, this one has a G nucleotide. The average would be 50% A, 50% G. Boom, like that. Makes sense to a computer, doesn't make much sense in reality because it's not a thing that can happen in reality. But there you go. Then you rerun the test. You say, okay, I've clustered these two. Now, what happens? And so now we might say that, oh, our new cluster is closest to this other thing. And we say, okay, great. We'll join those two together. And each time you run it, you keep joining it, and you keep looking for which are the things that have the least distance between them. Another feature, or bug if you like, of this tree is that it will always join all the sequences together, because it doesn't look whether the distance is so big that it might be stupid, meaningless, not real. It just assumes that you have put in homologous sequences, and that its job is just to join them together the best way possible. So here it's kind of dependent on the researcher doing a good job in screening what they have put in. So if you're not using something like a BLAST, something like an HHPRED, to figure out that these things really are orthologous or homologous or paralogous, then yeah, you're going to have a problem. Or rather, the tree will not tell you that you have a problem, but the answer will be misleading because it will show things joined together that really cannot be joined together in any conceptual way. Okay. And then you take that node, and that's a new node on the tree, and then you just keep grouping things together and saying, okay, the new node is in the middle of these two, and the new node is in the middle of these two groups, until you boom, 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 join together, and you basically arrive in the center of your diagram. And that's your average sequence, which is not a sequence that you can actually read particularly. It is a computed sequence that reflects all the genetic changes that occurred on the way to getting to that sequence, if that makes sense. So yeah, you connect everything until everything's connected, and then you're done. Yeah, congratulations. Yeah. Makes a lot of sense. Like you have a box of Legos in front of you and you just keep sticking them together, whichever ones seem like they go together, until you built something. Is it a good thing? I don't know. I don't know. We would have to look at it and we would have to assess it. We would say, okay, what else do we know about these organisms? Are they, do they both go through similar developmental changes? Do they both have babies in the same way? Do they both have fur and backbones or something like that? Are there particular traits that they share? And essentially, does this make sense given the rest of the data that we have? And if it does, then fine, we'll use it. And if it doesn't, then we'll say, maybe we should try a different method. So there you go. And here's our little example. So here's our distance matrix between these things. These are just arbitrary distances, but we're saying, so let's see, 5 and 4 are pretty close. So there we go. Our distance is 0.02. Great. 0.2. And 1 and 2 are really close. So here's the distance from 2 to 1. And so that's 0.1. You notice there's nothing on the top, but that's because these same numbers are over here. So the distance from 2 to 1 is the same as the distance from 1 to 2. And so we don't need to have another column here for 1 to 2, because we already have 1 to 2 there. Yeah, it's just a simpler way. You don't have to calculate everything twice. Okay, and here we're going to have, all right, here's the average of 1 and 2. And so it's going to be, we're going to say, all right, fine. So how distant is the group 1 and 2, like this circle, from each of these things? And we say, okay, it's about that distance from each one of these. And so now, in the first case, the lowest total distance is the one that you take, and those are the things you group. In the second case, you look at this thing and say, all right, what's the smallest number there? What's the least difference between these? And obviously, it's right there. It's the little red 0.2. And so that's the next one that the algorithm will join. Algorithms like this are fairly simple to write, fairly simple to run, fairly fast to run, and yeah, they do an okay job. Yeah, you can usually do better, but they're not always wrong. as you might think. And they mostly get you to the right spot. Here are the next steps. So we say, okay, fine. We joined 1 and 2. Now we'll join 4 and 5. And now let's see, what's the next distance? So we've got a distance between 4, 5, and 3. That's the next one. So we'll make a new taxon out of 4 and 5, the average of those, plus 3. And so the average of 4, 5, and 3 is going to be right about there, kind of on the edge of that circle. And we've already got 1 and 2 grouped, and so their average is right there. And so now we're connecting those up. And then we say, okay, now we have just 2 groups, the 1, 2 group and the 3, 4, 5 group. And here we can see it on the tree. 3 is a longer branch to 4 and 5 because they were close to each other. And 3 is more distant. And so 3 had a distance of 0.3 from 4 and 5. And so you see that's 0.15 up. And then 0.15 is going to be the total down. We're breaking it into 2 parts, but it's just the total down to the bottom. So there you go. If these are different lengths between 4 and 5, that's fine. You take the average of those 2 lengths and you say, okay, it's that far down to this particular cluster. That's the way the algorithm works. It's not the way nature works or anything else. It's just the way we're doing this for convenience. And then anyway, when you have the last 2 things, this group and that group, the only thing you can do with an UPGMA algorithm is you can join them together, and there they are, joined together, looking great, all in the same little thing. And so bam, that's going to be node number 9, where we join the 1 and 2 cluster right down here up to the 3, 4, 5 cluster right here. And that's kind of it. That's UPGMA. Yeah, and now you get a nice tree. And UPGMA is an automatically rooted tree because you're joining things together. The place where the last 2 things join is defined as the root. Is it really the root? Well, who knows? It depends what data you put in. If you put in a lot of data from a particular group or equal amounts from 2 kind of different groups, you may find that the root is halfway between them, but if you put in extra data that sort of was in between those things, you might get a more nuanced answer, or you might find that the answer is actually a little bit different. And something unexpected happened along the way in evolution, because of course evolution is a random process, and it's kind of hard to predict, except to say that things are going to change. They're always going to keep changing. So there you go. All right, and that's enough for this section. We'll go on to the next, which is going to be the neighbor joining method. This is just a little thing where you can measure the distance between these if you want with like a little ruler, and you could fill in all the little squares. And then you could say, okay, based on this, how would you join together the tree? And you could go through all the steps, and sure enough, you could definitely join the tree together. So there's our starting data. Here we put some little clusters on there. And so we made a lot of little clusters, and then we're going to try and join those clusters together. Great. And so now we're joining clusters together, and eventually we're going to work from a big table distance matrix down to a little tiny one. And as we do that, we're going to join the last 2 branches together, which is going to be this branch, C branch, is going to join to AEBFD branch. And there you go. You see what they're doing with the parentheses here? They're keeping things that are clustered inside parentheses. There's a major tree building or tree visualization method called the Newick tree, Newick, that kind of looks like this. If you look at a clustral result, look at the phylogenetic tree page and then scroll down a bit, you'll see a bunch of parentheses and a bunch of little distance numbers inside those parentheses along with what they are connecting to. Those parentheses are doing the same job as you see here. They're marking things that are very close, like A and E are close, so A and E are in here. And then A and E are next closest to B, so it's like A and E in the little bracket, B inside the next biggest one. D and F are in their own little group, that's great. And then you should put a set of parentheses around that entire thing to call it the AEBFD cluster, which they haven't done, but whatever. And then, there we go. We joined C onto it, and so we did it. All right. I guess, all right, last thing. So, UPGMA is going to assume, and this is worth knowing for sure, it's going to assume that the rate of substitution, the rate of change, is going to be constant for all branches of the tree. If that is not the case, you are not going to get a good UPGMA. Now think about that. You could have certain kinds of fruit flies. They can have babies every week and will die in 10 days, something like that. Some of them, may die even sooner than that. And so those are going to have a really fast generation time, and they're going to make changes every time they have babies. But over time, you're going to get a set of changes every week. Compare that now to humans, let's say. How many babies have you had this week? Was it 0? Oh my gosh, yeah. You're not working as hard as those flies. Huh. And we just can't. We take 9 months-ish to have a baby. And so we evolve more slowly because we don't make more changes, but we just have slower generations. And so the molecular clock, you could say, maybe goes at a different rate. We would expect things that have faster time in their generations to evolve faster. Things like viruses sometimes only take 6 hours, sometimes only take an hour to go through a complete replication cycle. They evolve really fast. Bacteria, it may only be an hour or two, a couple hours. So they evolve next fastest, along with archaea. And eukaryotes, there are some that are faster, some that are slower, and it generally correlates with how long the branches are on their phylogenetic trees. Things that evolve fast, go fast, and change more over time, because that's what we're measuring. So, as long as that assumption is true, as long as you're inside of a group that have fairly similar characteristics in this way, then you can use the branch lengths to estimate how long ago those two things were the same species. The sequence tree should mimic the taxonomic tree that he's calling a species tree here. UPGMA is always rooted by default. If there are unequal substitutions rate, you will have an incorrect root on the tree, and you can have incorrect branching on the tree, because things that evolve faster may have a greater genetic distance between them, even though they're both actually fairly similar to each other. So those are the caveats with UPGMA. Assumption of an equal clock, assumption of a root, which is kind of the midpoint of all the sequences, and assumption of equal substitution rates, which I guess is like the molecular clock assumption. So the other methods we're going to cover do not automatically produce a root, but you can specify a root based on other things that you know. Like you can take all the mammals and group those together and put in another group which is not a mammal, or which is a distant mammal. You can put platypuses or something like that, a really primitive mammal, early divergence. And the point where platypuses join on to all the cats and dogs and rhinoceroses, that's going to be about as close as we're going to get to the root. Or you could try and root it with frogs or fish or crocodiles, or with a whole bunch of things. Yeah. Rooting a tree is kind of an art in itself, and some people are real good at it. And generally, the more information you put in, as long as it is sensible information, the better root you're going to get out. And if you have a correct root, then you can interpret it correctly. And if you have a bad root, you will make bad, dumb decisions based on your tree. Not because you're bad, but because the tree is bad. So, there you go. Thanks very much.